Hello and welcome to Systems of Conic Equations. We're on Conics Packet 2, page 7. We got some real good problems for you today, and we will start it with a joke. The joke is, what do you call a man that was doing his trig on the beach? He was a tangent on the beach. Looking at page 7, I bet you're thinking, wow, we've solved a lot of systems in our day. We've solved systems of linear equations, systems of quadratics, systems of higher degree polynomials, and now we're talking systems of conics. And if you skip down to the middle of page 7, you see all the scenarios that could happen when you are finding out where two conic sections are going to intersect. No solution. They miss each other. No real solution. They could just be tangent to one another. Hit once, hit twice. You could actually have a conic. This hyperbola is going to intersect, looks like that ellipse, at 4 different points. But I defy you. I do not think there's any way to get any system of two conic equations to intersect at more than 4 points. You could have anything from 0 up to 4. For the first one, we'll take a little break. This is how we'll check our answers later in the examples. But for this one, it says use a graphing calculator. And I say while we're on the computer, why not use Desmos? So why don't we type these two equations in and just get some either whole numbers or approximations for the 0 through 4 possible solutions to this system. The first equation is what shape? Xy equals 6. Can you predict it? It's not like one of our traditional conics that has a transverse axis that's either horizontal or vertical. This one is like a y equals 1 over x graph. It still counts as a hyperbola, but it has that xy term on the inside of it. So here's a hyperbola, xy equals 6. And then the second equation looks like an ellipse, x squared plus 4y squared. What does it equal? It's supposed to equal 64. And we get an ellipse here. I'm kind of in the way. Looks like we got an example that's very pretty. I love how Desmos will give you like the coordinates of the vertices on the ellipse, and it'll give us good approximations for the intersection points. So I'm seeing at about 1.5 and 3.9, over at 7.5 and 0.8, and so on and so forth. So let's give that a try. We can go back to the packet and just list the solutions. We've got 1.5, 3.9. We've got the negatives also work. So negative 1.5, negative 3.9 was one of them Desmos gave us. The other two, 7.9 and 0.76. So I'll just round to the nearest 10, 0.8 and negative 7.9 and negative 0.8. So nearest 10th approximations for the 4 times that, oh, that was not good. The 4 times that those two conics hit. Okay, use that as a warm-up. Moving forward, if we can graph by hand to check, cool. If we want to use Desmos to check our answers, we can figure out if we got every single one of these correct. Now, what do you know? I give you the same exact system, but I say to solve it algebraically. I want to go over strategies today, and this one has an interesting one with all these decimal solutions. So think of a strategy. If you want to pause the video and give this one a try on your own, then hit play again, and we'll see if we can solve it together. I'm looking at the top, and it looks pretty easy to solve for either x or y. I'm thinking substitution might be a good way to do this, so I'll choose to solve for y. Okay. Today's lesson for the algebra lovers out there, you're going to get your fix. How about in the bottom equation? Can we plug that in for y? So you get x squared plus 4 times 6 over x squared equals 64. And we start simplifying, all in terms of x. So 4 times 36, you get 144 over x squared equals 64. And I'd like to isolate the fraction. So I'll get that by itself, and I get negative x squared, or 64, how about I say minus x squared. Okay. I'm going to get rid of the denominator by multiplying the x squared over to get 144 equals x squared times 64 minus x squared. And then we'll get rid of those parentheses. 64x squared minus x to the 4th. Looks like a 4th degree equation. It would be nice to have everything on one side of the equal sign, and I'd love for that leading coefficient to be positive. So I'll just subtract things over. I'll make this x to the 4th minus 64x squared plus 144. This is a quartic polynomial equation that can behave quadratically. So if it were to factor, we could solve it and factor it in a quadratic fashion. This one won't work out so nicely. I mean, we have a hint from the warm-up. The answers come out to be looking like they're irrational. So we're going to use, I'll put it in quotation marks, a little form of quadratic formula. we know that this isn't a quadratic equation, it's a fourth degree, but instead of saying what we're about to get is going to equal x, we'll say that it equals x squared, right? Quadratic formula should work here. X squared should equal what you get when you plug in a is 1, b is negative 64, and then c is 144. So x squared equals the opposite of b, plus or minus square root of, I didn't know 64 squared off the top of my head, I have to confess, but it's 4096, minus 4ac, so 4 times 1 times 144, all over 2. Okay, so we can kind of do this by hand. X squared equals 64 plus or minus. You get a discriminant that is 3520, all over 2. And then we get some decimals. This is where I would go straight to the calculator. X squared is going to equal either 61 point something or 2 point something, and regular x would be the square root of each of those decimals. So about, we could say, well, I guess I'll write x squared. This will make more sense if I do that. About, I'll approximately equal to 61.66. And x squared is also approximately equal to about 2.34. So to square root both of those, this is where my 4 answers are going to come into play. X is approximately equal to the positive or negative square root of each of these. So plus or minus 7.9, that should be familiar from what we got in the warm-up, and another x value of plus or minus 1.5. Okay, so those are good to know as x values. Your answers, your solutions to any system here need to have an x and a y involved. And I'd say this, one of your constraints back here is the easiest spot to go back to. Put 6 over each of these numbers. You're going to get y is approximately equal to what we got at the top, plus or minus 0.8 and plus or minus 3.9. So the way to write your answers, I'll say see the warm-up at the top, list it as a bunch of ordered pairs. These 4 ordered pairs turn out to work out pretty well as solutions to this system. Okay, I'm convinced. We got some good ones on the next page. Go ahead and turn over to page 8, and we'll start working in order here. Let me move myself down. And you have a system of what? A parabola with an ellipse. And they could hit a number of times, up to 4 times. So let's see how many times they hit. You decide on a strategy. Sometimes substitution is the best way to do it. Other times elimination is going to be better, but we're just having fun playing with the algebra by hand. I see x squared equals a nice easy expression here. So maybe we want to sub that y plus 3 in for x squared in the top equation, right? So I'll come down here and I'll say x squared equals negative y plus 3 is equal, plus, that was the next part, plus 4y squared equals 36. In one fell swoop, one substitution gives us a whole equation in terms of y. So you get 3y squared, not 3y squared, I'm sorry, combining like terms we don't have. So 4y squared minus y, and then I'll bring the 36 over and just say plus 33 equals 0. Feel free to use regular quadratic formula here. This is a quadratic. It actually will factor as well. We get a little luckier in some of the cases on this page. 4 and 1 would be good coefficients in front of the y, and then factors of 33. Turns out 3 and 11 will work if you go here and there. That should work out a 12 and an 11 product. Minus plus should give you that minus 1y in the middle. So 2 solutions for y. We get y equals negative 11 fourths, and we get y equals 3. Okay, those need to be accompanied by their x's. Feel free to plug back into one of the originals. I would say this bottom one might be a little bit quicker than the top one, less to square. So plugging back in, we'll plug in negative 11 fourths and get x squared equals negative 11 fourths. So 11 fourths should be just like 2 3/4, 2.75 positive plus 3. So x squared equals 5.75. X is going to equal the positive or negative square root of 5.75, right? And then simplifying that, you would get a 23 over 4, and it's square root of 23. That's what the inside would have been, over the square root of 4, over a 2. It's nice to get an exact answer. If that's possible and feasible over like a rounded decimal like we got on the last page, it's going to be preferred. I still have one more thing to plug in, but it's a bit quicker, I think. Just plugging in a 3 to maybe that bottom original equation. So x squared equals negative 3 plus 3. So only one solution for x here. X squared equals 0. Only thing I can think of for that is going to be 0. List your answers as a set of ordered pairs. There are how many solutions? Let's see. You have x equals plus or minus square root of 23 over 2 with negative 11/4. So that counts as two different solutions, positive and negative this x value with that same y, and then one more solution at 0, 3. I would recommend, if you have some time and if you want the practice reviewing, these are two that would be quick to just plot out by hand. You could graph by hand or on Desmos just to check to make sure we got the right answer. 3, I think, would be kind of quick, right? Look at that bottom equation. It gives us an answer for free. It says x equals, if I solve it, -1. This is great. We can take that right back up into x for this equation and handily get y. We'll go -1 squared plus y squared equals 49. And 1 plus y squared equals 49. So that means y squared has got to be 1 less than 49. And y is the square root of 48, which we can simplify. Since 16 goes into 48, its square root comes out. 4 square root of 3. And did I forget anything? I surely did. If we were to graph this one, and actually this one, I might take the time to graph it by hand because it's so quick. Two real simple equations dealing with -1. And then the y's are plus or minus 4 square root of 3 for that solution. So the check. Let's go review this one by hand. Up top, what is that conic section again? X squared plus y squared equals 49. Looks like a special type of ellipse where A and C are the same thing. It's going to be a circle. A circle, please don't judge. A circle of radius 7, right? And then look how quick the next one's going to be to plot. It's just the line at x equals -1. So maybe I'll use the line tool this time, and we'll do it in maybe a nice pumpkin. And we'll have it coming down and not really drawn to scale at x equals -1. So there are the two solutions we got. One at -1 positive 4 square root of 3, and one at -1 negative 4 square root of 3. I want to scroll down and take a look at number 4. All these are good, and all this is good practice with solving systems of conics, but I feel like substitution has helped us a lot with the others. And I'm looking at 4, the system of this ellipse with the hyperbola, and it wouldn't be too bad to eliminate either x squared or y squared. I'll say I want to get rid of x squared, so I'll have to just scale the bottom equation up by -2. So -2x squared plus 4y squared equals -24. And the top equation can go right above it. 2x squared plus y squared plus equals 4. And the x squared should be eliminated. You get 5y squared equals -20. Already feeling a little bit iffy about getting real numbers for this, right? Y squared equals -4 plus or minus 2i aren't real numbers that are going to show up on a graph. If you get any sort of equation when solving the system that involves imaginary solutions, just say there's no intersection point between the two conics. I put this one onto Desmos because these are easy to graph and check. I'll put myself right to the side. This is just too tiny of an ellipse to reach out and hit those two hyperbola branches, so the two conic sections just completely miss each other graph-wise, and then you don't have anything left. That's going to be it for today. I thought that was a good first couple steps in solving. I feel like all that hard work calls for a mini Dr. Pepper. So this is the moment I've been waiting for, and I hope you guys have a great day.